Welcome to Getting Started with InstaSPIN-FOC. In this video, we'll take a look at the graphical user interface that ships with each of the motor kits. Now let's look at the operation of the InstaSPIN-FOC GUI. The quick start guide for the GUI is going to walk you through all the details. So what I want to do is show you a demonstration of using the DRV8312 kit with the provided motor. This is a NEMA 17 24 volt, about 4 amp peak BLDC PMSM type motor. I'm going to go ahead and let the motor start identifying, and as I do that it takes about a minute and a half. You can follow along and notice the status changing here, going through the different states of the estimation. You'll also see some updates here to the resistance, the flux, and then the inductance. And while that's occurring, I'm going to go ahead and tell you about some of the other features on the GUI itself. So the default state of this GUI comes up in PMSM BLDC mode. If you do have an induction motor, you can choose the induction motor here. The identification method is set to automatic ID. In the future, once we release this project fully, you'd be able to actually save these settings of the identified motor parameters into your user.h file, and then if you want to use the GUI, you could compile that .out and actually load those settings directly here, bypassing this entire motor identification stage. The identification settings are critical for the motor that's going to be identified for a particular voltage, current range, speed of the motor, etc. Again, the quick start guide goes through all the details, and there's also some little helpful pop-up hints here for each of these settings. But please read through the quick start guide, and even the user's guide has a very thorough explanation of what each one of these critical values means. Here you can see that it has identified the DRV8312 kit. It actually, this exact same GUI and this exact same .out project that is loaded on the control card works for the high voltage kit, the 8301 kit, and the 8312. You'll see these hardware parameters are loaded for each board. So the 8312, the 8301, and the high voltage kit all have different hardware parameters. And these parameters are critical to some of the scaling that happens within each one of these solutions. You can see that my motor identification just finished, and for this particular motor I have almost 0.4 ohms. I have 650 microhenry of inductance, and I've got about 0.032 of flux. You'll notice in the control timing that this project is set up specifically to run with a 20 kilohertz PWM, and then we decimate all of the internal controllers, the A to D sampling, the current control, and our fast estimator down to 10 kilohertz. And this will work for the wide variety of motors, but certainly as you get up into two situations, if you get up into a lower inductance motor, which is going to have much higher torque ripple, you are probably going to have to up your PWM frequency to something to handle that. And then also sometimes with those motors in any very, very dynamic application, there are areas where you may have to increase your current control rate or your fast rate. On the flip side, there's also a lot of applications that aren't nearly as dynamic, and in that case we can actually run the current control slower, although 10 kilohertz is usually the type of update rate that we would run. But in some of these lower dynamic applications we can actually run fast quite a bit slower, 5 kilohertz, even 2.5 kilohertz. And all of these decimations can save you more MIPS and allow you to have more MIPS and more cycles left over for the rest of your project. So let's move on to some of the other tabs. The first thing that you want to do is go to the speed or torque tab. And this is funny, this little box here, this is the only time it's ever shown up with these little slide bars. On every other computer I've tried this GUI on, these are not there. So a strange little glitch in the system. But the first thing you want to do is look at these startup features. Since we just finished a new motor identification, the resistance has actually already been identified, and our offset, which is an offset for the ADC hardware where we do an adjustment, that's already been done as well. So we can go ahead and disable these since we just did a fresh motor identification. If you leave them, the RS recal is going to take about 8 seconds to do a full recalibration of the resistance, and the offset is a couple seconds to redo the hardware. You'll also notice there's a force angle start. You want to always leave this enabled the first time that you're starting up the motor, or anytime you're starting up the motor fresh from zero speed. This allows us to have a set point to where we force the startup initial rotation before our fast algorithm's feedback starts being used in the control system. And again, the user's guide, the quick start guide, has quite a few details on the capability and how you can change the set point of where this occurs. So with that, I'm going to go ahead and start up with all of the default values. And the first time you start up, there is a little 2-second probably pause here before it starts up. Beyond this, when I hit stop and start again, it'll start up immediately. You'll notice that the current controllers have some values set. These are set based on a few different parameters in the system, and the equations are given to you in the user's guide and in the quick start guide. So you'll notice that we came up running at 200 RPM, and I'm unloaded on this motor. So one of the first things I like to do is try to tune the speed controller a little bit. So the current control comes up in a set tuning based on all the parameters of the motor. We set the value, we find the bandwidth of the system, and then we actually divide this bandwidth down by about 4 for the KP gains. So as we get in very high speeds, we may want to increase these and make the current control even stiffer, but this is set for kind of the widest variety of applications. The speed loop, on the other hand, is not tuned at all. This is what we call a rule of thumb. There's a good engineering equation that we use to set these values that's based on the full-scale current and voltage of the system. So as you can see, I'm hovering around 200 RPM, although I'm not loading the motor at all. We should be able to run much slower than this. So what I want to do is first go ahead and set 0 speed. So this is a very unique thing that you can do. With most sensorless algorithms, if you try to set 0 speed and try to stay near 0 speed, the algorithm is going to crash. It's going to get corrupted with bad information. It will crash. You can see that we're attempting to hold 0 speed here, and we're actually doing an okay job unloaded already. We're hovering within a few RPMs. You'll notice the direction lamp is shifting back and forth, meaning that the algorithm is saying we're slightly positive or slightly negative of 0 speed. So I'm going to go ahead and touch the shaft of the motor here, and it's relatively stiff already. So this isn't too bad of initial tuning, but I'm going to go ahead and make it even stiffer. So I can increase these gains. And now if you try this yourself, you can definitely notice that the controller has gotten stiffer, and I am of course able to move the shaft. This is a small motor, it doesn't provide that much torque, but I'm going to go ahead and triple this value, and it gets very stiff. So now I actually have a sensorless algorithm here that is holding 0 speed. Now it's not holding 0 position, but it is attempting to hold at 0 speed. And this is a nice way to tune the system. If I really crank this gain up here and say go to 50, it's actually the motor, as I add a torque on it, you can see that the shaft, the speed loop really loses it. It's too aggressive and it's really gotten into an oscillation. So that means you've increased the speed gain too much. So here I'm going to go back down to a value that was stable. You actually usually have to go below the value, get back to a stable system, and I can crank these gains up. So this should be able to give me pretty good performance at low speed. And I'm going to go ahead and increase the integral, which is essentially the memory of the system here. And I have very stiff control. So now I can try to run a little bit slower. So with this motor, why don't we go ahead and try to run 60 RPMs. And I'm going to give a light load to the motor. I'm just going to put my hand on the shaft here. You can see that the IQ current is increasing. It's over an amp now, so I am providing torque. And you can see that I'm hovering around 60 RPMs. Not too bad. Now the next thing I want to do is obviously want to try to go slower. I'm going to remove the load from the shaft. You'll notice the torque signal immediately starts going down. I'm actually removing the load. I'm removing the load from the shaft, removing my hand from the shaft because I'm using a capacitive touchpad. And when you're using a capacitive touchpad and you touch the motor, the capacitive touchpad actually stops working. So your voltage changes and the mouse doesn't respond to you. So at 30 RPMs, you can see it actually dropped pretty low there. It's because there was no load. And so when there's no load, the back EMF is getting very small. And so I'm able to run here now a light load at 30 RPMs very well. One of the things to note when doing a test like this is that the DRV8312 board, the hardware, as you noticed, was actually scaled for over 60 volts. And we're only using a 24 volt motor. So one of the things to get even better low speed performance here is if you went and redesigned the hardware. So for your particular board, if you have a 24 volt board, make sure that you design the hardware for the highest voltage that you'll see for your motor. And this is discussed in detail in the user's guide. But if you did that with this motor, and we will have a nice 24 volt board later this year, you'd actually be able to see even better performance. So let's look at a few other things that we can do here. So we feel pretty good about the speed loop tuning here at low speed. Remember that as we increase the speed, these gains for the speed loop especially are going to have to be softened. You don't want to be so aggressive as you increase in speed. But let's go ahead and go up to a higher speed here. And I'm going to go ahead and increase. This motor can handle much faster acceleration. And you can see I'm already getting some instability because my gains at 0 speed are actually too stiff once I'm moving. So I'm going to go back closer to the original value. Remember my original value was 8, so I'm here about 50% higher, and you can see that I'm keeping about 500 RPMs here. So on this tab, one of the other things that you can do is go into torque mode. So torque mode, you can stop the drive, you can put it into torque mode. So this removes the speed controller entirely. And this is really a good way to test your system. If you're having issues and oscillation and maybe getting out of control, the first thing you want to do is take the speed loop out of the equation and really just test and make sure that your current controller, your torque controller, is providing the right response to any given step input. And so now that we're in torque mode, we can go and provide an input here. And remember that this is going to give you a constant torque, not a variable torque. And so if I just turn this on and have no load on the system, my motor is going to speed up. And essentially, as soon as you overcome the friction of the startup load, it's going to max out at full speed if it doesn't have a load. So if I do that and start the drive, you can see the motor immediately shot up and I'm going 5,600 RPMs. But I'm also keeping that constant torque input. And now as I load the motor, you'll see it go down. And just the load I'm providing with my hand is not enough. There's not enough torque to fully meet that. So you can see I'm getting some oscillation. So let's stop the drive again. Let's reduce this. Now I'm providing a load, and this torque is not enough to overcome it. So I have not increased my reference enough to overcome this load. So I'll loosen the load a little bit with my hand. And remember, we're not trying to control a set speed, so the speed will continue to oscillate. What we're doing is controlling a set torque point. And you can see with my IQ value in the middle of the screen, I'm right there at the set point. And the torque will go down as the motor gets faster. Okay. So I'm going to put this back into speed mode, and let's look at a couple other things that we can do. On the Speed Profiles tab, we have two different types of profiles. One is a staircase spin. This is basically a series of typically accelerations, so going from a low speed faster and faster and faster. So you can think of this like for a washing machine, as you go into the spin cycle, you end up spending just a little bit of time at the highest speeds and you slowly and slowly build up. You could also use this if you want to put in positive speeds and negative speeds. So you could actually have a staircase that's going clockwise and then counterclockwise, clockwise and counterclockwise. So you can set this up however you like. You just enter the various target speeds, the acceleration rates between them, and then the total time of acceleration and hold time in each one of these. And you'll notice at the end, this is, like I said, set up typically to do a full spin cycle up to very high speeds. At the end, we typically want to decelerate back to stop. The spin cycle is over. You want to make sure that you do this slowly. When you're going in these high speeds, and especially if you're using some field weakening, you're going to have a lot of voltage that can be dropped back onto the bus. And if you decelerate too quickly, that can go back onto your bus. And that's a system type of topic that you need to address in a real product when you actually make your final product anyways. Let's look at the agitation. So this is an interesting one that shows some of the good capability about the FAST algorithm, where we can actually accelerate to a clockwise speed or one direction, stop the motor, and go in the reverse direction. So these fields will set your target speed that you want to go to. In this case, we're going to go to 580 RPMs. We're going to accelerate at 580 RPMs per second. Remember, if you have a bigger motor, like a washing machine, you're not going to use values like this. In a direct drive washing machine, you may use 50 RPMs for your clockwise, and it may not accelerate in 50 RPMs. It's going to be very dependent on the linkage, the inertia, and any kind of load you have in your system. So be realistic about what it can do. Then we can set a hold time, so once it gets to that target speed of 580, how long is it going to sit there? So the ramp time to that speed, and then how long will it stay at that speed. And then we can decelerate at a given rate, typically the same. And then when you're doing these decelerations towards zero, there's a couple options. You can coast, so this actually means that you turn off the inverter and you just let the inertia of the system slow it down. And then it actually has a ramp, meaning driving it to zero speed. And then do you want to hold a particular time there? So this will be the total time to get to zero speed and hold zero speed before it starts in the opposite direction. So let's go ahead and see what this does. And again, I'm using the force angle to start up the motor. Once you've done that in an application like this, you have some options, and typically you're going to want to disable this. If you're passing through zero, you do not want this force angle to kick in. FAST can track nicely through zero, and it doesn't need the force angle capability. So I'm going to provide a slight load to this motor here, and in the top box you can see the speed reference, this positive 580 down to negative 580. And I'm actually holding slightly at zero speed, you'll notice. So I come to a slight pause at zero speed. And this shows very nice capabilities of the sensorless algorithm moving through zero. And you'll notice we pause slightly at zero speed before we take off. And FAST is tracking in this location and can provide the needed torque. If you pause longer at zero speed, you may get into a situation where FAST has slightly lost the angle. In that case, you may want to do something with using the force angle. And again, this is very motor dependent, very system dependent, load dependent, and so you're going to need to make these tests on your own. Again, the GUI is really for initial evaluation of looking at some of the capabilities of what this solution can do. Everything is going to need to be tuned specifically to your hardware, to your application, so make sure you keep that in mind. Let's take a look at some of the advanced features. On the Advanced Features tab, you can control the field control and change the SVM modulation. So let's do a little experiment with the SVM modulation. So in default, the SVM modulation comes up as 1.15. This is your maximum duty cycle. It's what we call the very top of the quasi-sinusoidal. So if you want to make sure that your output always stays purely sinusoidal, you could limit this to 1.0. But in each of these, until you move up, you're going to be limiting the average of the total voltage that gets applied to your motor. So if you want to be able to use the most voltage that's available on your bus, you want to increase this value, and this is going to allow you to go even faster. Now, one thing that you need to keep in mind is once you pass the 1.00, you're moving out of perfect sinusoidal. Once you pass 1.15, you're moving past quasi-sinusoidal into the trapezoidal region. And at 2.00, you're really commanding almost essentially a full BLDC trapezoidal waveform. So let's see what that actually does to our motor. So if we want, let's do an experiment. Let's put ourselves at the top of the perfect sinusoidal. And we can go back to our speed or torque tab. And here, let's put this into torque mode because we don't want to have to worry about tuning our speed controllers, especially up near end modulation. That may take a little bit of fine tuning. So let's just see what this motor can do. So in this case, we can start the drive, and you'll notice there's no torque input to the system right now. So give it a little bit of a torque, and it's going to go. And with full sinusoidal, we're running essentially 5,200 RPM. So this is as fast as the motor is going to go with that limit on the duty cycle. So we can stop this. So 5,200 RPMs. We can come back. Let's see where our quasi-sinusoidal Stops us. Come back. Start the drive, and we're at 5,600. So we gained about 400 RPM, so 8% or so. And now we can try moving all the way up into the trapezoidal. And coming back, so we had 5,200, 5,600, and now we're at 6,400. So from the sine wave up to the full trapezoidal, we've gained over 1,000 RPMs. So over 20%, which makes sense based on the relationship to the sine wave and the full trapezoidal wave. So this is one way that you can get more speed out of your motor, is really using the available voltage bus that's there. And you probably can't hear it, but the sound when you move into the trapezoidal does change significantly from a sine wave. It does become noisier, and that's something that you have to think about as a trade-off in your system. Now, one of the other ways that you can increase the speed is to use field weakening. So let's do a little experiment with our field control. So I've set my SVM modulation back to the default of 1.15, where we could go up to about 5,600 RPMs. So I'm going to increase this acceleration a little bit and go ahead and get up near where we need to go. And I already know that the speed control is going to have to be detuned a little bit, so it's not quite as aggressive at high speeds. So let's go ahead and start up the motor and get up towards our peak speed. Remember, with this SVM modulation, we could reach about 5,600 in torque mode. It'll probably be a little bit less in our speed mode here. So let's go ahead and command 6,000. We know we shouldn't be able to reach that. We're nice and stable. We're getting as much as we can, right about the same as the torque mode, 5672. So if we want to increase this up to 6,000, we already saw that we could change the SVM mode, move into a trapezoidal region, use more of the bus voltage. You can also use field control. So what I'm going to do here is slowly add some ID current. It's actually a negative value. Always put in a negative value. And by adding a little bit of negative ID current, you actually weaken the magnetic field that is being produced by the motor itself. And this will allow you to reach higher speeds, but at the other side you're going to be reducing your torque. So if I had a load on here, if I had a full load and I tried to do this, the system would probably end up stalling it, right? So you can't be operating in your full load condition. It is a trade-off between speed and torque. As you notice, with a little bit, 0.2 amps of ID, I'm able to go up to 5,800, so let's see what it takes to get up to 6,000. I'm almost there, 5,900, so I bet a little bit more gets me there. Almost, so let's go with half an amp. So with half an amp, I'm able to actually cross the 6,000. And you'll see my gains are set a little bit. It's going to come back down, and there I am at 6,000. So it's a nice slow-moving speed control here at this point. And I can go back up in speed again and try to go higher. Let's say I want to go to 7,000. Right, with the field control, with the ID that I have on here, I can still only go a little over 6,000, so I can start increasing this myself. We also offer an auto field weakening, which will dynamically change and adjust the ID up to the maximum of whatever you set here as your max. On the small motor that comes with this kit, it's kind of hard to do automatic field weakening because the magnets, because the motor can move so quickly, it pretty much saturates and immediately will command all of the ID, even though it's not necessary. So for a small motor, a demo like this, you'll want to use the manual field control and just inject it a little bit at a time. For a larger motor and for applications where you typically use field weakening, like on a big torque machine, like a direct drive washer, or for transportation drive control, you'd be able to use the automatic field weakening to dynamically adjust this ID current up to your limit. So if we want to keep trying this a little, we can go ahead and get up to 7. Go ahead and put some more on here, and it's probably going to take more than an amp, so let's go ahead and move up. Getting closer. And there I am. I made it over 7,000. I think we'll come back down. Our speed loop will drive it back down right at about 7,000 like we want it to be. So we're getting a little bit of oscillation here, so what I would do in this case is actually come back to the speed loop and make it a little less, and you can see now we're pegging in right on 7,000. So So this is one of the things you have to do in a real application with field weakening. The speed loop becomes even more critical, and you are going to have to tune this yourself and really set up what we call gain staging. You're going to have different gains at different speeds and at different load considerations to give you the dynamic performance that you desire. Now, when you're coming out of field control, what you need to do is be real careful, because while you're pumping current into this motor, it is heating up, and you are running high speed, you're producing quite a bit of back EMF from the motor. So whenever you're moving out of field weakening, you want to be very careful. So one of the first things you can do is command a speed lower than where your field weakening kicks in. And of course your speed controller will bring you down to that 5,000 nice and steady. But you're still actually putting ID current into the motor. So here's where you want to be careful. And depending on your motor, you may need to do this very slow. And on some motors, you could just do it in a couple stages. But you want to do this kind of gently. If you try to just command 0, all of that extra voltage is going to come off of the motor onto the bus, and it potentially could upset your system. So I think we've waited enough. We've drained most of that off, and we can move back to 0. So we're at 5,000. We're back under control. No field weakening to worry about. So now if we want to command 0 or go ahead and stop the drive, we can do so. And with that, I hope you have fun experimenting with InstaSPIN-FOC and the GUI. I think the important takeaway at this point is that you can't try everything on the GUI. This project does not cover all PWM frequencies. It does not cover all voltage and current scalings that are going to make your motor perform the best. This is really a demonstration purpose of the technology, and what you want to do after this is you should be convinced that this is compelling technology, and you should take the next step of looking at the user's guide and moving on to the motorware-based projects. So I appreciate your time, and have fun spinning your motors with InstaSPIN.